Today we're going to start applying everything that we've learned about stoichiometry to some very specific chemical reactions, which is the whole point of what stoichiometry is all about anyway, because just finding the amounts that you have of something doesn't really do us any good unless we can do something with those amounts. So we're going to, the next little step that we're going to take today is looking at a chemical reaction and saying, all right, if I have this amount of this piece, how much am I going to have of the other piece? So the sample that I'm going to use today is this rather complex looking equation that I have up here. This is actually the first step in a process of converting pure iron, or converting iron ore into pure iron. Now, I don't get all the way to pure iron in this particular reaction because this is just the first step in it. So this is the iron ore. It's iron sulfide. And so if the manufacturer starts with a certain number of moles of this iron ore, how many moles of oxygen is he going to need in order to be able to complete the first step of this process? Now, the interesting thing about these chemical reactions is that when you use them, you can figure out, if I know just one of these, either one of the reactants or one of the products, I can either calculate how much of the other reactant I will need, or I can calculate how much of the products I am going to end up with. And I'm going to use that all by doing mole ratios. Now, here's a very, very key point that you have to keep in mind when you're doing these problems. You've already learned that the coefficients, the 4, the 11, the 2, and the 8 in this particular equation, you've already learned that those coefficients can tell you how many atoms or how many molecules are going to react with one another. Those coefficients can also tell you how many moles of each will react with each other. They never tell you the ratio of grams to each other. So you can't ever use this to convert grams to grams. You can only use it to convert moles to moles. Okay, so let's take this example problem that we've been given here. So I've got 1,256.0 moles of FeS2. And just like any other type of problem I'm working, I take that and I'm going to put it over 1. The question is, how many moles of oxygen am I going to need to be able to react all of this so that I don't have anything left over? Okay, now every other time that we have set up a conversion factor with moles, we have said that we always have to use the number 1 for the mole because we've been converting moles to grams, or we've been converting moles to number of molecules or moles to number of atoms. So in those cases, it's always 1 mole. But this situation is different because I'm trying to find moles of one reactant to moles of the other reactant. So I'm not going to use 1, I'm going to use instead the coefficients that are in this equation. I'm trying to get rid of moles of FeS2, and I'm trying to find moles of oxygen. And again, you can tell this is different because I don't have the same compound both on the top and the bottom. Here they're different. Okay, so moles of FeS2 from the equation is a 4 down here, and moles of oxygen is an 11 from up here. So moles of FeS2 will cancel out. And so when you type this into your calculator, 1256 times 11 divided by 4, and that will give you 3454.0 moles of O2. Okay, when you're looking at significant figures, you're always going to take and use what you started with because these are whole number ratios and they would actually have an infinite number of significant figures. And it's exactly 4 moles of the iron sulfide, it's exactly 11 moles of the oxygen from the balanced equation. So again, number of significant figures you have is based on the number of significant figures that you started with. Let's look at the second equation here, or second part of the problem. How many moles of iron oxide, the Fe2O3, will be made? Well, here you can see that in this problem I related the reactants to each other, but I can also relate the reactants to the products. So I'm going to start with the 1256.0 moles of FeS2 because, again, that's what they gave me. And if I have a choice, I'm going to tend to stick with what they gave me as opposed to what I calculated up here, just in case I happen to make a mistake so that I don't carry that mistake through someplace else. Okay? From the balanced chemical equation, I need to convert moles of FeS2, and this time I'm looking for moles of Fe2O3. Okay? From the balanced equation, since I'm looking for a ratio here, the FeS2 has a 4, and the Fe2O3 has a 2 in front of it. Moles of FeS2 will cancel out, and so type it into your calculator. It's 1256 times 2 divided by 4, and that should give you an answer of 628.00 moles of Fe2O3. Okay, so in today's assignment, no grams involved. We're doing only mole conversions using chemical equations.